Hello, today we're going to talk about ionic and metallic bonding. So let's start out by reviewing what an ionic compound is. Ionic compounds always consist of at least one positive ion and at least one negative ion. So remember that positive ions are called cations and negative ions are called anions. And cations are positive, anions are negative. And so what happens is the positively charged ion attracts the negatively charged ion. And that force of attraction between oppositely charged ions is called an ionic bond. And so sometimes you'll see it called like electrostatic attraction or electrostatic force. But what it boils down to is opposites attract each other. Opposites attract. Now, I want to remind you guys about a shortcut that we can use to find the most common ion on the normal or representative elements on the periodic table. So there's your general periodic table. The elements in group 1 tend to form a positive 1 charge. Group 2 will tend to form a positive 2 charge. Group 13 tends to form a positive 3 charge. Group 14 could go either way. It could form a positive 4 or a negative 4 charge, although they don't form ions all that often, but it could go either way. Group 15 forms 3 negative charges. 16 is 2 negative, 17 is 1 negative, and 18 doesn't form charges usually because those are the noble gases and those are completely stable. So we can use this shortcut to determine the most common ion of an element in any of those groups. Remember that the transition metals are in that middle section of the periodic table, and they can form different charges depending on the situation. And so you'd have to use context clues to figure out the charge, and we're going to talk about that today. So again, ionic compounds form between a positively charged ion, like in groups 1, 2, and 13, and a negatively charged ion, like in groups 15, 16, 17, and that when the opposites are attracting, they form that ionic bond. Okay, so ionic compounds form in what we call a lattice structure. Lattice. And so what that means is it's an alternating pattern of positive and negative ions. So I'm going to attempt to draw as best I can here. So if I have positive charges and then negative charges, they're going to be alternating because the positives and negatives want to attract each other. But if you have 2 positive ions, they're going to try to repel each other. Or if you have 2 negative charges, they're going to try to repel each other. So they wind up arranging themselves into this 3D arrangement where the attractive forces and the repulsive forces kind of balance each other out. And now this is in 3 dimensions. I'm not the best at drawing in 3 dimensions, so imagine it like forming a cube of this or a crystal of this instead of just a 2D flat image. And so what we wind up with is what we call a formula unit. Now in this case, there is 1 of the positive charges for every 1 of the negative charges. So you have a 1-to-1 ratio of positive to negative. An example of this kind of compound would be sodium chloride because you have 1 of each. And so that's what we call a formula unit, is a ratio of the positive to negative ions in an ionic compound. Now, this is going to be distinct from covalent compounds, but effectively, we don't know if we're going to count these 2 ions as our ionic compound, or if we want to count these 2 ions as an ionic compound. We don't like distinguish between them, but we know that it's always in this ratio of 1-to-1, which is our formula unit. Now you can have other ratios. Another example would be something like calcium bromide. Calcium bromide always forms in this 1-to-2 ratio of positive to negative, and we'll talk about why that is in a minute. But again, it's going to form this like 3D structure, so it's impossible for us to look at like a one distinct compound. It's just going to be this ratio of ions. Okay, so how do the ionic compounds actually form? We're going to be starting with neutral elements. So let me use an example. I'll use lithium fluoride as an example. Okay, so lithium is in group 1 on the periodic table. So it has 1 valence electron. We're going to draw like this, and this is called a Lewis symbol, where it just shows the valence electrons. Okay, and so lithium has 1 valence electron. Fluorine is a halogen. It's in group 17. It has 7 valence electrons. And so I want you to get in the habit of putting 1 on each side before you add a second one. So there's fluorine, 7 valence electrons. Now, whichever one is the metal is going to lose its valence electrons. And whichever one is the nonmetal is going to gain valence electrons to fill up its shell. And this is a kind of a review of what we call the octet rule. So lithium is the metal here. It's in group 1. It's going to lose its valence electron, and it's going to transfer it to the empty spot on fluorine. And so you'll be left with lithium, lost an electron, it forms a +1 charge. Fluorine gained an electron, so now it has 8, and now it has a -1 charge. And now because they're oppositely charged, they attract each other to form our compound lithium fluoride. And so that's how ionic compounds form. There's a transfer of electrons from the metal to the nonmetal. Let's do a few more examples of this. So sodium is in group 1 on the periodic table, has 1 valence electron. Chlorine is in group 17. It has 7 valence electrons, 1 on each side before you double up. The metal transfers the electron to the nonmetal. And so we have our compound is sodium chloride. Another one here, potassium with oxygen. Potassium is also in group 1. It's 1 valence electron. Oxygen is in group 16. It has 6 valence electrons. Okay, so the potassium is the metal. It's going to transfer its electron to an empty space on oxygen. But wait a minute, there's still an empty space. We can't leave it like that. Remember we talked about that 3D lattice where there's many possible positive ions and negative ions? So what happens is another potassium atom gets involved, and you can add it in, and it's going to also lose an electron to fill up the other empty space in oxygen. And so we wind up with all of the potassiums have lost their valence electrons. The oxygen is completely full of valence electrons. And to get that to balance out, we use the compound K2O because it took 2 potassiums to balance out 1 oxygen. 2 potassiums, 1 oxygen. We don't usually write ones. Let's look at 2 more examples here. Calcium is in group 2 on the periodic table, so it has 2 valence electrons. Chlorine is in group 17. It has 7 valence electrons, 1 on each side before we double up. Calcium is the metal, so it's going to lose its valence electron and fill in that empty space on chlorine. But chlorine doesn't have any more empty spaces. It is completely full. It has its 8 octet rule. But I still have another electron in calcium. What I can do is add another chlorine in. Chlorine has 7 valence electrons. And so I can transfer that other electron from calcium into an empty space on chlorine. Now the calcium lost all of its electrons. The chlorine has completely filled up with valence electrons. And so my ratio, there's 1 calcium for every 2 chlorines. Last one, aluminum and sulfur. Aluminum is in group 13. It has 3 valence electrons. Sulfur is in group 16. It has 6 valence electrons. I'm going to transfer from the aluminum, because it's the metal, over to sulfur. So that one can fill in. This one can fill in. But I ran out of empty spaces in sulfur. Let me add in another sulfur. Sulfur has 6. I'm going to transfer the other one from aluminum over to sulfur. But wait, there's another empty space in sulfur. That's a problem. Let me draw another aluminum. Aluminum has 3. I can transfer one of those into the other empty space on sulfur. But wait a minute, I still have 2 more electrons on aluminum. I can add in another sulfur. Now I can transfer the electron from aluminum to an empty space on sulfur, from the aluminum to an empty space on sulfur. And now it is balanced out. All of aluminum's electrons from both of those atoms have been transferred to all of the empty spaces in those 3 sulfurs. So my ratio here, there are 2 aluminums for every 3 sulfurs, and that makes a balanced compound. Now we talked about the positive and negative charges forming a lattice structure. That lattice structure has various strength based on something called Coulomb's law. Coulomb's law is influenced by 2 things: the magnitude of the charge and the distance between the 2 things. Okay, I'm going to put in parentheses size here. All right. So let me draw in, I have my lattice. I'm going to draw a slightly smaller, well, we'll just do it like this. Okay, positive and negative ions in an alternating lattice. Now, if I have something that has positive 2 charges, they're going to be stronger than positive 1 charges. So the larger the charge, the stronger the attractions between the ions. Or if I have like a negative 2 charge, that's going to attract more than a negative 1 charge. The other thing is size. So think about how far away things are, distance. If I have 2 ions that are very close together, so positive and negative charges are very close together, they're going to attract very strongly. But if I have a positive and negative ion that are much further apart, that will attract more weaker attractions. So size, if you have atoms that are much, much bigger, they're going to have weaker attractions than ions that are smaller, because ions that are smaller can get closer together. So the larger the size, the weaker the attractions between the ions. And so this is important because it's going to determine things like melting point, boiling point, and just overall strength. So increasing charge or decreasing size is going to make those things have a stronger attraction. Okay, so I just wanted to mention, we talked about the lattice structure, but I wanted to show you kind of what it would look like in 3 dimensions because I'm awful at drawing in 3D. But this would be an example of like a 1-to-1 ratio for an ionic compound. You see that alternating 1-to-1 structure. This would be an example of a 2-to-1 ratio. And so it's going to have a slightly different structure, and that's going to also affect its macroscopic structure. So that's where you get all of these crystals that have some really, really cool shapes and colors. And it's a whole field of chemistry. It's very interesting. But so that the charge and the distance between the ions also affects their like 3-dimensional structure through their crystal lattice. All right, let's also talk about polyatomic ions. Polyatomic ions. Let's break down that word. The prefix poly means many. Atomic, so many atoms. And then ion in an ion. And ions have a charge. So polyatomic ions means there are many atoms in an ion. Now, there are 8 really common ones that we're going to use in honors chemistry. These are listed on your formula sheet. but you should be familiar with them. Carbonate is always CO3, and it has a 2 negative charge. So let's look at that one first. This is where you have carbon attached to 3 oxygens, and I'm not going to draw the full out structure, but this whole thing has a charge of -2. So it can bind to something like with a +2 charge and form an ionic bond that way. So it behaves like a single ion, even though there are multiple elements present. Phosphate is PO4 with a 3- charge. Sulfate is SO4 with a 2- charge. Nitrate is NO3 with a 1- charge. Acetate is C2H3O2 with a 1- charge. Chlorate is ClO3 with a 1- charge. Hydroxide is OH with a 1- charge, and ammonium is NH4 with a 1+ charge. These ones are just the common ones. There are many, many, many other polyatomic ions that exist. These ones are just going to be the ones that pop up most frequently. If there are any others, I will always give you like the name and the formula and the charge on like a particular question. It will be embedded in the question. So now let's practice actually forming the full compound using those polyatomic ions. So if we're going to do sodium with chlorate, okay, now when chlorate has that -1 charge, sodium is in group 1. So if we look at our shortcut for our charges, sodium's in group 1, it has a 1+ charge. So you'll have to like fill in the charges for that. What I can do is make the charges match. So if I have sodium, which is a 1+, chlorate, which is a 1-, do the charges match? Yes. So that's nice. They can just form a compound, NaClO3. Done. Let's do another one. Sodium with carbonate this time. Sodium has that 1+ charge. Carbonate has a 2 negative charge. Those charges do not match. I need an additional positive charge so that my overall adds up and cancels out the negative charge on the carbonate ion. So 2 positives cancel out 2 negatives, and I would write that formula as Na2CO3 because it took 2 of the sodiums to cancel out the CO3 ion. Let's look at 2 more examples. Calcium this time. Calcium is in group 2 on the periodic table, so it forms 2 positive charges. Bromate, I told you here, is a -1 charge. It's not one of our common ones, but I gave you enough information to be able to solve the problem. Now, the charges do not match. I have a 2 positive and a 1 negative. I need an additional negative charge to cancel out the 2 positives. So what I'm going to do is add an entire ion. Okay, I can't just add a bromine. I can't just add an oxygen. I have to add the whole thing. So now I have a 2 negative charge that can balance out the 2 positive charge. And so I'd write my formula Ca. Now this is different. Whenever you have more than one of a polyatomic ion, I'm going to use parentheses. BrO3, and I have 2 of those. Think of it, I have 2 sets of the bromate ion. Let's look at another example like that. I have NH4 ammonium, which has a +1 charge. Oops, and H4 with a +1. And I have phosphite, which is PO3 -3. This is a different one from phosphate that we saw on the previous slide. But we have enough information here to solve. I have a +1 charge and a -3 charge. They don't match. I need an extra ammonium. Well, now I have +2 versus -3. They still don't match. If I add in another NH4, now they add up to +3, which cancels out the -3. You always write the positive one first. Okay, so I'm going to use parentheses, NH4. I have 3 sets of NH4 ions to cancel out the PO3 ion. And so that is my formula unit for ammonium phosphite. All right, let's shift over and talk about metallic bonding. In metallic bonding, we have only metals, no nonmetals present. So you're going to see positive ions. And the biggest thing about metals that you should know is that they have valence electrons that are free to move. We call that delocalized valence electrons, which means they are free to move. This makes metals have particular properties. So they can conduct electricity as a solid. They become malleable and ductile, which we will talk about more next. Malleable, ductile. They also tend to have pretty high melting points and boiling points because of that attraction between the positive ions and the negatively charged valence electrons. Metals are also governed by Coulomb's law. So the larger the charge, the stronger the attractions between the metals and the electrons. Also, the larger the size, because they would be further apart, that would lead to weaker attractions. Between the positive ions and the electrons. So Coulomb's law still applies to metals, as it does with ionic bonding. Okay, so what about malleability and ductility? Malleability means you can shape or form the metals. A good one to remember would be like aluminum. Most people have had some experience with aluminum foil. You can, roll it up into a ball. You can bend and shape it. Another one would be like different types of wires that you can bend and shape, or like a paper clip you can bend. And so that's malleability. Ductility is the ability to draw it into a wire. To form the wire at all is ductility. And all of this arises because of those free valence electrons. Just draw like this. So because the electrons are free to move, it allows us to bend the metals around. So I could like shift this, do a very quick drawing. I could like shift part of it to bend it and shape it, and the electrons are still moving, and it's not going to just break and shatter like an ionic compound would. Because ionic compounds have that alternating lattice. If you try to apply a force to it, then it's going to activate those repulsive forces. But the electrons here are free to move, so they kind of move along with it as you're bending it, which is really cool. So all of this kind of combines into what we call the metallic model, which has a sea of mobile valence electrons. With the sea, there's like free flowing, free to move valence electrons. And so if you haven't yet drawn it in your notes, you should draw the positive ions that are the metal ions and the electrons going in between them. And they're not stuck in place. The electrons are free to move throughout, which helps it be good conductors of electricity, helps it to be bent and shaped really easily. Last thing for today, we'll talk about our alloys. Alloys are mixtures of metals. So if I have my metal ions like this, and I have my valence electrons moving around, what is fairly simple to do is to take one of those metal ions and replace it with a totally different type of metal. It can just fit right in, or it could fit in between the spaces. And so when you have different metals mixed together like that, that's called an alloy. Some common alloys are things like brass or steel. Stainless steel, bronze is another example. Brass is an alloy of copper and zinc. Steel is usually iron with things like, it could be mixed with carbon, could be mixed with chromium to make stainless steel. There are other things. You don't need to memorize any specific alloy, but we often mix metals together so we can get better properties. They might be stronger or rust resistant, depending on the mixture. So things like stronger, rust resistant, or more dense. And so depending on the application, you might choose different metals to put in your alloy.